All right. Thank you for being here. I already briefly introduced me at the beginning, and today I want to talk about something which just really for a couple of years I've paid attention and gotten more interest, and that's kind of hopefully will explain also why I was so excited about the opportunity that we got through Iris and other funders to have us all come together and talk about light. Because I'm thinking more and more about light, the importance for physiology in a broader term. So my background comes from invertebrate vision, and so for most of my life, I've been chasing insects that have really peculiar visual systems that work kind of maybe in different ways. And I still do this, and I continue to have a fascination. In one of my scientific highlights has been working with this weird creature, which since then has been gotten attention from engineering, and they now produce some cameras which are based on that's actually multiple projects. So I'm just throwing this out because I think this is super cool. This is kind of the dream of having basic research which suddenly turns in something real applicable and great. But when you work with animals, you also notice that light becomes important because you have them in the lab and they will not behave until you do something, somehow give them a better light environment. And so I've gotten very, cautious about this. And in order to figure out what kind of light we have, we need a very important tool, namely a spectrometer. And once you have a spectrometer, it's actually a real fun tool. And so I had my face where I would take it with me everywhere and point at light sources. And of course, those are the sun. So this is the sun spectrum. And y-axis is intensity. I'm glad, Dan, that you mentioned about intensity not always being the best measurements, but for some reason, for this particular curve, I can't get it to display something else. Also, we can measure it in terms of photons. So if I integrate between 300 and 700 nanometer, which seems a reasonable spectrum because it's for our visual system, then we have about 8 to the E of 6 tons photons, kind of in the outdoor environment on a sunny day. On a cloudy day, it's a lot less. It's about 2 to the E of 16 photons. And so you can see it's considerably less, but it follows the same general curve. But then where it gets really kind of disturbing is when you go to an indoor environment. And I'm not talking about a dark environment. Actually, I measured this in my very own office, which generally looks relatively bright. But then you take the same spectrometer and you measure the office, and suddenly you kind of need to put on your magnifying glass because you barely can see it at all. It's somewhere, this little wiggles then would be the indoor lighting. And I have a fluorescent bulbs. For those who've looked at spectrum, probably you already figured this out because it has this characteristic couple of peaks. So very, very clear difference. I don't think I need to explain anymore. Those pictures are worth 1,000 words. That definitely is a very strong difference in intensity between like even a cloudy day and the indoor intensity. But the second issue is that the indoor spectrum is missing critical portions of the spectrum. Again, you saw those few wiggles, and there are a lot of places where there's no light at all. So again, looking at the human visual spectrum, this is just from a textbook. We have three short, like a short, medium, and a long cone. Those are our color sensors. And then we have the rod. So that's the visual color detect, also visual systems input channels, if you will. Now, if you overlay the spectrum, again, this is the spectrum from my office, just over there. What you notice is actually, well, we all notice our light in the office looks relatively white, but, and for good reason, so because all those photoreceptors are excited in some ways, but again, we're missing some intensities in between. And if you think that maybe newer lighting, like LED lighting, is better, then it has actually its own problems. In some ways, it's better. This is a typical spectrum from a so-called white LED lamp. And again, it's actually really good to give us white light, and it's super practical for vision because it excites the short wavelength. So this is the main peak, and then there's this phosphorus, which captures some of this and emits it in a longer wavelengths, and so makes the wave light look white. And Morgan, if I did this incorrect, please correct me. But that's my understanding of a LED, and that's actually a super clever mechanism. It works really well to give us something that looks white. But there is a problem. Well, I'll go to the problem for a moment. I have started to get to think as the body more as a light sensor, because so this is great because this facilitates vision really well. But thinking as the body more of a light sensor, there are other places where this may play a role, and I hope I can explain this in the next couple of slides. So a lot of it is actually known in terms of how specific wavelengths are influencing our physiology, starting with vitamin D production. Of course, you all know that vitamin D is a really important vitamin for us, and it's produced in the skin, and it needs a little light. But of course, there's this trade-off, especially the light that is actually needed here is very, very short wavelengths light in the UV. And if you get too much of it, you sunburn, and then there's cancer risk and so forth. And so we tend to smudge ourselves with sunscreen in the first moment that we go out in the sun. And at the end, what do we have? We have a big epidemic of vitamin D deficiency, actually globally. And that epidemic doesn't really even affect everyone equally, leads to a whole array of negative health effects, from cardiovascular disease, cancer, osteoporosis, neuropsychiatric diseases, autoimmune diseases, infectious diseases. There are all sort of papers which show this. So that's the first wavelengths that I want to point to. The second one is based on this opsin, neuropsin 5, and I expect that Dr. Richard Lang will talk a little bit more because that's right his field of expertise. But it's fascinating literature about that opsin being important for circadian clock, but also for eye development, including some studies which showed that cataract replacement lenses, whether or not violet light is transmitted or not, makes a difference there for develop or preventing short-sightedness. And so that's a really cool and interesting wavelengths. Then we have the actually generally better known melanopsin, OPN4. That has a peak around 480 nanometer, and is important for regulation of our internal clock, but also for other things such as the pupillary reflex. And I haven't ever anything found about it, but sometimes I've been in a bright, really bright internal kind of lab environment, and it's really great because it's nice and bright, but like something is off, right? And I think that one thing that might be off is that our pupil doesn't constrict the right way, because the pupil doesn't have the right light wavelengths of light to adjust to what otherwise is relatively bright. There has been linked to mood disorders and then dopamine levels. So blue light for the circadian clock also, this is where I wanted to now point out to this problem about our normal lighting. If you go back to the LED, beautiful design for us to see. It's designed for vision itself, right? But this wavelengths just happen to fall exactly through the cracks here. And I think so that's one issue to consider. And then last but not least, there are all those long wavelengths. And there's a really interesting hot patch of literature of this possibly promoting health. There are multiple different mechanisms that have been proposed, and I've been fascinated by this. Now, I say hodgepodge because some of it is more circumstantial, but there are actually really some fascinating studies. One that has caught my attention is one from Mark Hideman's lab in Detroit, where he has a heart attack model of rats, where he basically deprives them of oxygen and then revise them, and it turns out that like about 85% or so of the neurons may die, or 86%, it's right there. And then if he has a certain infrared light that he shines on it during the reviving these, then suddenly he can reduce this to only about 35%. So I saw infrared light has a real strong protective action there. And so that is fascinating also, because there's a proposed mechanism, and that has to do with energy production in our body, which is mediated through the mitochondria. And so our energy unit is ATP. And so between sugar and ATP, this is like the most sophisticated chemistry laboratory with many steps. But a key enzyme for one of the steps is called cytochrome oxidase C. And it's considered the rate limiting enzyme for all this chain of reactions that have to take place. And interestingly, cytochrome oxidase C has a copper in it. And that copper happens to absorb light somewhere from 700 nanometer to 1 micrometer. And that is fascinating, because if it absorbs light, energy is being transmitted, and it's then not so surprising that it may do something. And so they mapped out that it seems in certain wavelengths, it seems to inhibit, and in other seems to accelerate the action of this enzyme. And so maybe this recovery has something to do with it. So in my lab, Michael Meese, somewhere around here, oh yeah, right over there, has started to spearhead a project on Drosophila where he is exposing them to very bright light, blocking out the photoreceptors, and then using different wavelengths of infrared light to try to get them to recover. So the paradigm is 3 days bright light. Then they cannot see, which we can establish by measuring the photoreceptor response. And then he has a paradigm of 10 days of recovery. And this is what he gets. First of all, the bright light indeed knocks out the photoresponse. So here you see the 3D controls whereas the light damaged. And then on the y-axis, you see the photoreceptor activity. So you're higher on the y-axis, more healthy, if you will, the photoreceptor. Also, the better they respond. And so this would be the control. The bright light wrecks it out. Not so surprising. Well, then he has the 10 days of recovery. But in the 10 days, the flies also age. So now he needs a new control. And it turns out that actually as the flies age, their photoresponse goes down. But it's still better than the photoresponse of those which had the 3 days of bright light. And then they had 10 days of recovery and just some sort of background light. We give a little bit of a background light to help the circadian clock, because photoreceptor activity changes by day and night. And so we need to make sure we have fair measurements and that they keep the circadian clock. But here comes the amazing part of his data. Now add 2 other wavelengths of light, and suddenly you get a much stronger response. So we have 810 nanometer here and 850 nanometer there. And in both of those cases, remarkably, actually, if you think about this, these now do better than the normally aged equally old days, which didn't even ever have any trauma to light exposure. So those wavelengths actually can help them to recover. And then he looked at 950, and that was unexpected. Those two are absolutely miserable. Like the 950 meter light kind of doesn't help them at all. And in fact, basically photoreceptors don't respond. So this is very different, because it's the opposite finding than the Hüttemann group did for his heart attack studies. But then when you think about it mechanistically, there may be very good reasons. I think both studies point to the fact that there's something really interesting happening with the modulation of this molecule and some of those processes. Happy to talk to you more about some ideas of why this may be. But in the light of time, I want to just move on and say that I think there is a lot more to be done in those near infrared and infrared kind of wavelengths in terms of how physiology might be influenced. And then last but not least, I like to play with electronics and try to start kind of making my own light bulb by putting together a whole bunch of different wavelengths of light, and then this particular bulb, after I put in what I think should be put in, it was all way too blue. Then I had to put some amber in there. But in the end, I got something that looked relatively white, but now has an extended spectrum. And then here, That's a little circuitry. My brother's electric engineer. He made that for me. So I can play with it there. I can drive different channels with different intensities. So we can have a more intensive, more extended spectrum. So this is the beginning of how I dream that maybe a light could look, and any input in that direction or expansion would be great because, because it relates to my overarching question, which I'll show in a moment. But just to conclude, we evolved in a light environment that's about 200 times brighter than the environment in which we spend most of the time. Indoor lighting lacks physiologically critical wavelengths because the lighting industry has designed lights for the process of vision. And I think there is a good reason to possibly extend that. And so there's a better need for lighting. And so this is my key question that I'm most interested to get more input and discuss is how should the light of the future look like? And I put poor climate change inflicted Earth next to it, because in any of those designs, of course, we want to be mindful. At the moment, like Dan showed, we have way too much light in places where we don't want that. And then we don't have enough light of some of the critical wavelengths in places where we do want that. And there must be a way to solve both problems without actually causing a big burden on the overall energy budget. And that's all I have. Yeah.
Because crucial question you touch on, I think there is now an emerging very strong case for completely changing the way we do material mapping. Even the design equipments to recognize all this biology. I'll talk a little bit more about this. There is a very interesting case of red light therapy for myopia.
For myopia.
It's really, really interesting. It clearly works. It has a dramatic beneficial effect. But it is one of these long wavelengths that you described. So it's another example where we really don't know how that works, but it does.
Wow, that is fascinating, because again, of the myopia, thinking of the very short violet light, I also think maybe we gotta think a little bit about the ratios of light. So for me, again, with evolutionary biology history, I was thinking, what's the actual overall spectrum that we're involved with? And we, until very recently, we spend most of the time outdoor, right? And so suddenly we're spending indoor. And with myopia, that's a big issue because it's hugely on the rise. It's clearly correlated with being indoor. There have been studies that show just like 2 hours extra outdoors can slow it down during development and such. So yeah, that is fascinating. I would love to.
Yeah, I suspect in the long run, we have to get the timing of spectral composition right, and we probably also have to get the wavelength distribution relative to a horizon right as well.
Right.
So it's a little bit complicated.
Right. So and then right, exactly. So it needs to change to adjust during the time, and then according to Dan, now we know also we need to change it between top and bottom. So probably the way we super actually exciting, enormous opportunity there. But one of the problem is that when you Google lighting fixtures, for example, they all tell you sunlight, broad spectrum, complete spectrum, whatever. And then I bought so many light bulbs and put them in a spectrometer, and then they're nothing was promised. There were, I don't even know. Yeah, sure. Yeah. See?
I was thinking, so as a preemie in the 70s, I know that at least back then, they used to put babies in little cages with extreme light. Has there been any studies for that in the long run, right? Is that, developmentally precarious? They have a little band on you, but that was really effective. I put mine off regularly.
So Billy Rubin, yeah. Right.
Right, but still light, yeah.
Yeah, so UV light, actually it's amazing. Even things with psoriasis and stuff through the skin, UV light is very useful for some of those things. But the Billy Rubin jaundice in the babies is, but yeah.
It's a big issue. I mean, there are clearly light things development.
Elke, you strong that. What wavelength is it?
The strong light.
This light that you're exposed to is about 520 nanometers. Oh, actually, blue. It's
For the audience,
yeah,
420 is close to violet. It's 480.
it's 480. Yeah. For blue.
If you're asking for the Christopher,
Oh, the wavelengths from our very bright light. Yeah, so we tried first with some LEDs so we could get it really well controlled, and that wasn't quite enough. So we have a combination of LED light and fluorescent bulb light. It's not, if you ever can give me a white, truly white light for these things, well, yeah, we have the spectra. We can show you the spectra. So so it's a combination of fluorescence and a white LED. Yeah, so that's really, really interesting too. If it has too much short wavelengths, that is destructive in itself. Although that's actually something that came up twice with your talk and then in our evening conversation, the whole thing about the high energy of UV light. And yet a lot of insects have UV photoreceptors which somehow survive that. And I know for us humans, our lenses shield out a lot of the toxic UV content. So that's part of what fosters cataract. But my understanding is, and Richard correctly, that the retina is relatively protected from UV light because the lens takes it out, right?
Yeah, there's actually a development stage to UV transmission.
Uh-huh.
So early, there's more UV transmission than there is.
Right. So earlier, more UV transmission, and then it's blended out. And yet, insects, photoreceptors, at least those which can respond to UV light, it has to get there, right? So how are those photoreceptors actually not, with all the energy, how are they? I mean, we know that too much light can be damaging, but I would be interested if the machinery that protects, that's there for homeostasis in a UV receptor has to be much more than what's in a green receptor, for example. That would be interesting. I hadn't thought about this before until your comment. Huh?
When in the discussion, how do you expect the newborn babies generation? This kind of reason is probably going to make a few other things. So would you expect
Well, yeah, so that's great because that's a great transition into Richard's talk. I probably used up way my time or beyond, I don't know. So yeah, thank you. Now I'll have a switch. I'm gonna just end stream and start again.